So, we looked at the 4 position motion generation, and we will briefly look at, just for completeness, we will look at the case of a slider crank, synthesizing that for 4 positions of the slider. Okay. So, I can again use the diode form. So, say this is okay. So, you have Z1, Z2, and if this is the path is given by a vector S, I can specify the displacement of the slider as rho j of S. So, this will be e power I phi j, and then this will be Z2 e power I gamma j. So, again I can write my loop closure. My loop closure will take the form Z1 e, you can confirm that this is the case. Okay. Where S is the vector specifying the path, the vector specifying the path. So, I just need a scalar to say how much it has displaced along the path. Again it is in the standard form. For the 4 positions, you will have to again solve the compatibility equation, which we saw earlier. So, you will have rho j is just a scalar that specifies how much along the path. So, it is a factor, because this is from the initial position how much it has displaced, a scalar times the vector that designates the path. So, I have the compatibility equation just as we did earlier, and this will be rho 2 s, rho 3 s instead of the deltas that we had for the motion generation. Okay. This is equal to 0. So, if it solves the compatibility equation, so for combinations of phi 2, phi 3, phi 4, so if I choose phi 2 as my free choice, solve for phi 3 and phi 4, again you will get the same 4 bar loop closure compatibility equation. You will get delta 1 plus I phi 3 plus delta 4 e power I phi 4 equal to 0. So, if you solve this equation, then you will get combination. So, you can again do the same thing that we did for this. Okay. So, 4 position function generation with a slider crank is not really. Gammas are given, or in this case actually the phi's may be given. So, it depends, if you want to coordinate the input motion, either way the form will be the same. Okay. In which case you will take gamma 2, solve for gamma 3 and gamma 4, that may be more likely actually, because usually you will coordinate the slider displacement. So, yeah, in this case, okay, let us say phi j and rho j are specified. So, you would actually do this in terms of gamma 2, gamma 3 and gamma 4. Yeah, that makes more sense. Okay, so you will find the what are the angles of the connecting rod or coupler that will give you the, that will let you solve the equations for Z1 and Z2. Okay. So, you will solve, once you solve the compatibility equation, you solve for Z1 and Z2. Okay. So, the diode synthesis method is very flexible. It can allow you to design many kinds of mechanisms, including multi-loop linkages as we saw. So, you can extend that method and use it for motion generation, function generation, path generation, prescribed timing, etc. Lots of and with an analytical method you can build in other things into your design. For instance, for every mechanism that you choose, you can compute the minimum transmission angle, for instance, or if you want only a crank rocker, you can, when you have an analytical routine, you can go through design choices more quickly. Setting it up takes a lot of time, but if you are going to do, go through a number of these, then it makes more sense to put in the initial effort to use an analytical method. Also, it is going to be more accurate. So, if accuracy is something that you are looking for, obviously the graphical methods are not very accurate, and you are also limited in the number of positions that you can synthesize for. Again, analytical methods also give you the, we saw with the blocks method, for instance, you can connect velocities, angular accelerations, etc. So, if that is important for your application, then obviously an analytical method is what you want to go for. So, as you saw, most of the analytical methods are based on the vector loop equation, and the use of complex numbers makes that very elegant because you can express rotations nicely with complex numbers. So, that kind of concludes what I wanted to do with analytical synthesis. Now, although we have also dealt with path generation. So, path generation also we saw that it is a matter of specifying, in fact, it is easier to do than motion generation, and you can actually synthesize for more precision points because you are not worried about the orientation of the coupler. But the next topic that we shall do is coupler curves. Okay. So, coupler curves are essentially path generation. You are looking at the path of coupler points and how to use that for your design, but they warrant separate treatment because with the precision point synthesis that we have done, we are only looking at specific points, but there are some characteristics of the curve itself which can prove quite useful when you are looking at applications, and that is the reason we will look at coupler curves in a little bit more detail. So, if you look at the 4 bar, you have the crank, you have the rocker, and you have the coupler, which is the floating link. The crank and the rocker are pivoted to the ground, but the coupler is the one that is floating. We call it the floating link in the plane. And so, that is really the most interesting link in the 4 bar, because the crank and the rocker, all points on them trace only circular paths. Okay. So, there is nothing exotic there. But if you look at, so if you take this, so if I have a 4 bar like this, OA, AB, OB, and I assume the coupler is this grid that is attached to AB. Okay. So, if I take different points on that grid, as the 4 bar moves, they can trace some very interesting curves. So, if I take this point C, okay, I get like a sort of a kidney bean shaped curve. something like this, little fancier. Then I can do like a teardrop. So, this point F on this grid, as the linkage moves, traces this kind of a teardrop, and then I can have sort of a figure 8 with this point E. So, you can have some very interesting paths, and you can use portions of these paths for very interesting applications. So, that is the nice thing about coupler curves. Slider crank, again if you look at the coupler, same thing, you have the grid, different points, you again have a figure 8, you can trace different paths. In many cases, the use of coupler curves can enable you, this is a very special application of coupler curves. In many cases, they trace approximate straight line paths. Okay. So, in places where you may have had to use, see the problem with a prismatic joint is the maintenance of it. First, manufacturing it to a certain level of precision is difficult, and then maintaining it, because if anything gets into it, the prismatic joint can really stick. Okay. Revolute joints are a lot easier to maintain. So, if you can do something with a linkage with only revolute joints, that is a better option than going to a linkage with prismatic joints. So, early on, the fact that some coupler curves can trace approximate straight line paths was used extensively for designing linkages where you wanted, like for instance, this is a portable drill, and this can actually, so this coupler point can actually trace that straight line path. So, they are using a 4 bar to do this. So, this is the 4 bar OA, OB, OA, AB, OB, and this is the point that traces an approximate straight line path. Then dwell mechanisms are another common application for coupler curves. So, what is a dwell? Do you remember what a dwell is? Right. So, the follower, you have an input and an output. So, even with a continuous input, the follower, the output remains stationary for a period of time. This is very useful in assembly or packaging or those sort of applications, where something comes on the assembly line, it stays for a little while where some operation is done to it. Okay, you may have boxes moving, and when the box is at a particular location, they need to slap a label onto it. Okay, the dwell in the mechanism gives you the time. So, it is still the boxes are continuously moving. Okay, you have a continuous input, the box comes at an instant where there is a dwell in the mechanism, you put the label onto it, then it moves away, and then so it is very useful for those sort of applications in the assembly line. And here is a nice animation of this. So, we can use the coupler curve or the coupler point, the coupler curve to design these kind of dwell mechanisms. So, here look at, you have theta in, okay, and you have theta out. Okay. You see that for a certain period of time, theta out remains more or less the same. Okay. This is so, if you look here, you can see this link, it does not move. When does that happen? Okay. You see here that this link, this point is tracing the coupler curve. Okay. So, D is a point. So, this whole thing is a link, ABD is one link, as you can see, they are not two different links. Okay. You have to be careful, that is one link. So, D is a coupler point on AB. Okay. So, and D is tracing this path, and it so happens that this portion I do not know if I can write, oh okay, this portion approximates a circular arc. So, what happens? It means it has a constant radius of curvature. So, if I pin a link, this link, okay, with a length equal to that radius of curvature, then when it comes to that point, right, this point E does not move, and if E is connected to the output link, then the output link remains stationary as this point D is traversing that circular arc. Now, we would have seen dwell linkages, many designs based on cams. Cams are a common way, and it is a very easy way also to introduce dwells into mechanisms. Again, cams have the problem of, because it is a higher pair, right, maintaining lubrication in the joint is difficult. So, if you have, and so wear can be high in cams, and which of course changes your output for the mechanism. So, if you can do it with a pin jointed mechanism, then it is, of course cams are of course more compact. So, it again depends on your application. That is really where the type synthesis that we first talked about comes in, because you have to consider a lot more factors when you are designing something. This will occupy a lot more space, obviously a linkage, but if you can use it, then the coupler curve gives you a nice way of going about designing a dwell in the linkage. Here is a coupler curve that actually can do two dwells. It is a double dwell linkage. Same thing, in this case you have two portions, okay, of approximately the same radius of curvature. So, with the dwell with this kind of linkages will not be like a perfect dwell. So, there will be some jitter possibly in the output link, it will not be perfectly stationary, but if that is acceptable for the application, then it does not matter, again depends on what the need is. Okay. So, this is another good example of using coupler curves, and this is something that, I mean, you could design, you could specify points that would fall on, but you can't really say, see with the if you do the precision point synthesis, I can specify points, but I can't really say how the linkage will behave as it moves between those precision points. Coupler curves give me a little more control over that, because the curve is a continuous curve. So, I have an idea of how that is going to be traversed. Another example of coupler curves is in intermittent motion mechanisms. Okay. So, this is called a called a walking beam or a beam transport, box transport mechanism, walking beam transport mechanism. And what it does is, so it uses, so I have, it's just, this is actually an 8 bar, but the basic unit, the driving unit is a 4 bar, OA, A, B, OB. Okay. Fix OB and OA are fixed to the frame. Then you have a point C, a coupler point that traverses this kind of a curve. So, what you do is you attach this link, couple it to another linkage parallelogram, so that the same motion that this linkage follows is also followed by this linkage. You have only one driving crank. Okay. And then this coupler curve, so it, as it moves along this point, okay, essentially this transport arm moves those articles, okay, then it follows this path, right. So, it moves down on that path, comes back, then moves the next set of articles out. Okay. So, you get this nice intermittent motion for this mechanism. Okay. So, this is another example of the use of coupler curves for your mechanism. Okay. So, because for the coupler curve you have to look at the whole thing. Okay. There is something called the Hron's and Nelson Atlas of coupler curves, which has about 7,000 mechanisms and their coupler curves. So, this is like an atlas with over 7,000 coupler curves of various shapes, and it is a very practical tool because it includes all crank rocker mechanisms. So, they can all be driven by, so it is all Grashof 1 crank rockers, okay. And they give you a choice of about 7,000 coupler curves that you can select. So, the notation that is followed in that atlas, the crank is always of length 1, then you have the coupler length is given by A, B is the follower length and C is your fixed link. So, based on this you can find, so the atlas will be something, a page in the atlas will be something like this. Okay. So, you have to imagine, so if you look here it looks a little confusing, but this is your so when we talk about coupler curves, we refer to AB as the coupler base, because you are looking at other points, you are really interested in. So, we do not talk of AB alone as the coupler, we call it specifically the coupler base, because the point that you take may be something. So, if you look here you can see a grid. So, you can see equally spaced points. Okay. And then it tells you what kind of curve that point is going to trace as the crank rotates in the mechanism. Okay. So, that is what, so if I look at, if I choose A and B, it is obvious circular path. So, they are not, the coupler curve for that is not marked. If I choose this point, okay, and I construct my linkage, so I connect, if that is the coupler point I choose, then what this atlas tells me is, as this linkage, as the crank moves, this point is going to trace this curve. Okay. And the dashes, okay, you have these dashes that give you an indication of the crank rotations between the points. So, if for equal crank rotation, okay, so I think 10 degrees, yeah. So, for every 10 degrees of crank rotation, this would be the distance traversed by the coupler point. Okay. So, that means if I look at this curve, so if I look at this coupler point and I look at this curve, where is it moving, on which part of the curve is the point moving faster? On the top part, because it is traversing more distance for every 10 degrees of crank rotation. So, you also get an idea of what the velocity of that point is going to be. Okay. So, let me show you. So, there is a nice interactive atlas, which is what I was trying to download and install. Let us hope it is done. Okay. So, this tells you that these are the coupler curves, the crank is always 1. So, OAA is 1 unit, A which is the coupler, or the coupler base AB equal to 2 units, then OBB equal to 2 and OAOB is also equal to 2. You can see this is a Grashof linkage and the crank is the smallest link. So, it is a crank rocker. So, I can now try to scale it. So, I can now measure this distance, measure the location of this coupler point P. From this, scale it up accordingly. Okay, it will be an approximation, but you can get you get a pretty close. The coupler curve that you will get will be close to that. Now, there are some special curves here, as you can see, some of them which have these kind of sharp, these are called cusps, or if it traces a figure 8 here, this is called a crew node, that point where it is crossing over itself, right, that is called. So, these are special points called cusps and crew nodes.